So let's see, well, the technique seems to work. Good morning, everybody. This is already day 3 of a tremendous conference, and we're just waiting for the organizer to appear that we can start out. Probably JAUME asked me to sit here that he could go out, have a nice morning, but anyway, it's a great pleasure to introduce to you today's speakers. So first we have Wright from Harvard University, and if I remember correctly, he just some time ago made it over the border from the Canadian side to work with Peter Gallison as a postdoctoral fellow at Harvard University. And then we will have Dennis Dirks on the program from Utrecht. And well, I guess it's now 5 past, half past. Well, we were just waiting for you. I tried to tell jokes, but that's not what I am really good at.
Then I'll crack a joke myself, if this works. Just one thing, I just spoke to the secretary, Martin and some of you. You didn't receive an invoice with what you paid for the accommodation. Throughout the morning, she's going to, you have it already on your invoice, Martin, and now, I mean, she just clicked on your inbox, sorry. So you'll get a bill with what you paid for the accommodation and everything. If you don't by lunchtime, please let me know and I'll just complain, because tomorrow they're not here. So any admin stuff that we need, please let me know today, right? And now you can start.
Okay, so let's start. Our first speaker, Wright, will present a talk about moments on ontological indecision in Paul Dirac's transnational correspondence network. It's 45 minutes, but you should not consume more than half an hour so that we can really try to track things down.
Does this work?
Yeah.
Does this? Yes. Okay. Great. All right. Well, thank you all very much for coming, and I'm happy to be able to bring a small piece of my work to an audience that will be so knowledgeable about the people and subjects that I'm talking about. This is a small piece of I guess, my larger project that was in my dissertation. My dissertation was on the theory of, or theoretical pictures of the vacuum and empty space in quantum field theory and also general relativity. And I start with Dirac, and I go up until about 1980, talking and ending with Yakov Zeldovich. My chapter on Dirac is about the changing ontological pictures of the vacuum that is engendered by his electron theory, and the related issues that are alive in the literature about mathematical beauty, the relationship between sort of epistemological and aesthetic concerns, and the ontological changes. But today I'm not going to talk about mathematical beauty. I'm going to talk about the community of physicists and a small zoom in on correspondence and how correspondence, personal visits, and publications interacted in the debate sort of immediately following the introduction of Dirac's theory in 1928. And at the end, I'll have some. Historiographical remarks about the use of correspondence in the history of physics and the history of quantum mechanics, and how perhaps we could use correspondence as another way of building a link to broader concerns in history of science, not just in the history of physics and quantum mechanics. So just a very brief reminder of Paul Adrian Maurice Dirac and his dates. British, of course, Cambridge. He then retires to Florida State University, and the archivist there negotiated with Clare College, Cambridge, to ship all the original documents away from Cambridge. So if you want to see these letters, you have to fly to Tallahassee, which is a bit of a strange choice. I don't really understand why. He probably could have gone many other places, but he chose Tallahassee, Florida. And of course, the Nobel Prize was 1933, specifically for the work that that I'm talking about today. So the brief overview as the Dirac electron circa 1928. He says it's a point, not a sphere, mathematical point. He's using a Hamiltonian formalism to describe it. He's finally found a way to reconcile this Hamiltonian desire with Lorentz invariance. He is happy that he thinks that his solution to the problem of the electron is the simplest possible mathematical construction that satisfies his requirements. So he's very happy to have this aesthetic criterion met. It's consistent with his transformation theory developed by him and Jordan in 26 of quantum mechanics, and specifically he was one of the requirements for his theory for his development was that the Born interpretation of the square modulus of the wave function holds in his theory. This was his biggest problem with the Klein-Gordon equation, that the square modulus could be negative, therefore it could not be interpreted as a probability. And here Dirac said, well then, what good is it? We need this interpretation so we can make connections to the empirical world. So he was very happy to have this. But then, of course, he found that this four-component wave function that is a vector that interacts with the 4x4 Dirac matrices that he introduces requires this interpretation of negative energy solutions. And so what will he do with these negative energy solutions, and what are the consequences of this is sort of what follows. Okay, so there is a debate about you could call ontological, metaphysical, philosophical consequences of his theory. How seriously should we take this? How do we deal with these strange negative energy objects? And in the time period from 1927, when he first sends a preprint of this paper to Bohr's Institute in Copenhagen, until I think I end up in 1932, this debate goes on, and it's the media in which this debate happens are letters, preprints. Dirac is actually quite the world traveler in this period, and then also formal publication. So there are debates happening at different levels, some varying by how visible they are to if you are not in this immediate community of elite physicists who are, roughly speaking, connected in this sort of network. And the main issues that were discussed, sorry, if I turn more this way, the microphone is. The main issues that were discussed are what to do with these electrons, protons, holes in the sea of negative energy particles. Issues about space and time and quantum mechanics and quantizing space and time were coming up, and perhaps some people are surprised this is a little early for quantum gravity, that sort of thing. Particularly, Vladimir Fock, we'll see, was concerned about intra-theoretical consistency. So if there's an infinite number of negative energy things that have mass, why can't we see them? And then also, we'll see that the stability of atoms will come into play as well. So I'm not going to put a lot of quotes on the screen. I'm going to read them to you. But this is just a very rough picture of Dirac and sort of the center of his world, major figures, and roughly where they are. Okay, so Oscar Klein recalled that Dirac sent a preprint of his first electron paper to Copenhagen around Christmas of 1927, and already at that time, the theory was being connected to new ideas about space and time. Niels Bohr wrote to Dirac on 27th February 1928. He says, "Dear Dirac, I feel very ashamed first now to write and thank you for your great kindness in sending me an abstract of your last most wonderful paper. I need not say how deeply interested we all are in the new development, which it surely will open. Klein has been especially interested in various points concerned with the general ideas of space and time and is very eager to get opportunity to discuss them with you." And here, of course, Bohr is referring to Klein's five-dimensional theory. Dirac submitted the electron paper on 2nd January 1928, and it was published 1st February. It made an immediate impression in European physics centers. From Hamburg, Yoshio Nishina wrote, "I must congratulate you on your great success in obtaining a complete solution of the electron. We are all looking forward to your paper in the Proceedings of the Royal Society." And Werner Heisenberg wrote from Leipzig on 13th February, "I admire your last work about the spin in the highest degree." Dirac visited Heisenberg in Leipzig in June 1928 and gave a lecture on his new theory. And the only real records of this lecture from the archives or anywhere else are two edited versions that are translated into German and published in sort of minor local Leipzig publications. So the language may not be the most precise here, but the general framework of what he said is evident. Dirac motivated his presentation by noting the requirement that in order to have a sensible electric charge density in a theory, the Hamiltonian must be linear in the time derivatives. Perhaps at Heisenberg's prompting, by summer, Dirac realized that the positive energy solutions on his theory, which initially he just said, oh, these exist in the first paper, we'll just ignore them. But they can't just be ignored. But he did not have a solution in view. At the end of his talk, he briefly turned to, quote, the difficulties inherent in the current theory that are still far from being solved. He recognized what we would now call the charge symmetry of his relativistic equation. If, quote, if we write the wave equation minus E instead of E, one should, as a result of the now very different physical problem, get a much different wave equation. Well, in fact, nothing new results. Perhaps the set of four solutions, two more than necessary, could be divided into two groups, one group for each charge of the electron, but again, this would only work if there were no transitions, but they were allowed. However, he said, these are going to be very rare. The probability of them is very small, suppressed by a fourth power of the speed of light. And so he says, consequently, the present theory, his theory, is an approximation. Right, so this is sort of an interesting view because it's taken that Dirac had this very solid sort of faith in his work, but here he's saying, oh, well, perhaps it's just an approximation. He concluded the lecture with the sentiment that a major change in outlook would be necessary to fix the problem, and connected it to the metaphysics of space and time. Quote, it seems that this problem can be solved only through a fundamental change in our previous idea, and perhaps is related to the difference between past and future. And so here perhaps we see a connection with what Alexei was discussing earlier, that when faced with a problem, he says, maybe we need to reinvent the wheel, the world, everything. Right. It seems an open question to me whether Dirac at this stage was considering physical interpretations of the positive energy states in his equation. The most conservative reading, I think, is that he was not at this point. Rather, he saw his theory as a mathematical approximation, valid for a certain range of electron velocities smaller than the speed of light, and saw a need for reworking the entire physical picture at play. Right? But as Dirac's work percolated throughout the international community of physicists, his simple abandonment that he had expressed in print was further called into question, and famously Hermann Weyl published two papers while he was in the Institute for Advanced Study at Princeton around the middle of 1929, suggesting that these solutions should be identified with the proton, that really Dirac had found an additional, his theory was not just of the electron. And there's no indication that I could find in Dirac's papers that he considered the possible physical interpretation of this before Weyl, so it may have been the sort of Göttingen mathematician who had first made this proposal. But the issue of how to do this was on his mind. So on 24th July 1928, Dirac wrote to Klein, I have not met with any success in my attempts to solve the plus or minus E difficulty. Heisenberg, whom I met in Leipzig, thinks the problem will not be solved until one has a theory of the proton and electron together. By winter 29, we know he was working on a physical interpretation to engage with Weyl. Bohr wrote on 24th November that from Gamow, I hear you are now back in England again, and that you have made progress with the mastering of the hitherto unsolved difficulties in your theory of the electron. As we have not yet heard about any details, Klein and I should be very thankful if you would be so kind to tell us something of your present views. Bohr's view was that the difficulties in Dirac's theory might be said to reveal a contrast. This is a quote between the claims of conservation of energy and momentum on one side and of the conservation of the individual particles on the other side. Now, Dirac was not in the habit of keeping outgoing correspondence copies, but of course his well-known reply was saved by Bohr for 26th November. And again, connecting to Alexei's talk where he talked about Dirac and some seeing some experimental evidence, as Alex mentioned, and calling into question conservation of energy, Dirac, in his reply to Bohr, says his own opinion of this question is that Dirac should prefer to keep rigorous conservation of energy at all costs, and would rather abandon even the concept of matter consisting of separate atoms and electrons than the conservation of energy. But then Dirac would continue to say perhaps he has solved the problem, right? And he brings in this picture of the Dirac sea of the negative energy particles. So he says in his letter, assume that the wave equation that I had published previously is correct. And he says, let us now suppose there are so many electrons in the world that all these most stable states of the negative energy electrons with high velocity are occupied. The Pauli principle will then compel some electrons to remain in less stable states. For example, if all the states of negative energy are occupied and also a few of positive energy, these electrons with positive energy will be unable to make transitions to states of negative energy and will therefore have to behave quite properly. The distribution of negative electrons will, of course, be of infinite density, but it will be quite uniform, so that it will not produce any electromagnetic field, and one will not expect to be able to observe it. So this is the first statement of this picture of the Dirac sea, the vacuum of these infinite particles, infinite density of particles. It was calm, so contrary to the contemporary picture where the sea is this foaming, bubbling piece coming out of people like Wheeler. This was a calm sea and unobservable. And he suggests that holes in the sea, making an analogy to Heisenberg's theory of X-ray orbits, would act as the protons. And this was the view that he published on 1st January 1930. So this paper comes out. He has expressed it directly, personally, to the Copenhagen group via Bohr, and you can assume that there would be some discussion and passing around of this interpretation. Then it comes out very quickly in the Proceedings of the Royal Society. Dirac's correspondence expressed a mixture of admiration and doubt about his new theory. Even before the January paper was published, so on 7th December, so perhaps in another communication that was not saved, or perhaps through Bohr's Institute, Heisenberg wrote to Dirac expressing these emotions. He says, "Dear Dirac, many thanks for your letter. I heard about your new paper already a few days ago from Landau via Gamow. I think I understand the idea of your new paper. It is certainly a great progress. But I cannot see yet how the ratio of matter, etc., will come out. It seems to me already very doubtful whether the terms of the electron, the Sommerfeld formula, will not be completely changed by the interaction with the negative cells. One may hope that all these difficulties will be solved by straight calculation of the interaction, and in this case it would probably be necessary to treat the interaction in a proper relativistic way," and he references his paper with Pauli, which Dirac was not a big fan of. Dirac sort of thought, well, I played this game and I won, and I don't really understand why you and Pauli are going off and sort of redoing what I did already in this sort of uglier, less aesthetically pleasing way. After the paper was published, Heisenberg wrote again on 16th January, "Dear Dirac, many thanks for the reprint of your new paper. I have calculated a little about the effect of the interaction of the electrons in your theory. In this calculation, I have used the formalism of quantum electrodynamics, which Pauli and I have worked out. From section 2, I conclude that you're, etc., familiar." So he says, the problem is the electron and the proton get the same mass. Now, there's some arguments in the literature about Weil being the first one to express this, and Weil was the first one to express this in print, but actually Dirac was aware of this before Weil's publication. There's some arguments about how it was this sort of group theoretical symmetry argument that convinced Dirac that this would be the case, but this is prior to that. But Heisenberg goes a little further. He says, it is possible in principle to construct interactions in which the electron and proton get a different mass. In this case, however, the ratio of the masses becomes infinite. So, you were right maybe that if we just calculate it, we could get a different ratio, but I did it and disaster. It's an infinity. So Heisenberg concludes, I feel that your theory goes very far away from any correspondence to classical laws and also from empirical facts. And Pauli may have sort of established this independently as well. In, I think, a more convivial engagement, Igor Tamm, who was Dirac's friend and hiking companion in Russia, wrote on 3rd March 1930 identifying a different problem with Dirac's theory, the lifetime of an atom. He writes, I was very much interested in what you write about the probability of the annihilation process, especially as I was just working out this probability myself when I got your letter. And Tam says that considering this positive energy electron and a hole in a volume, he finds, by analogy to the scattering calculation that Dirac put in his 1930 paper, so here's certainly one genealogy of relativistic quantum scattering problems is from this work by Dirac, which is then picked up by Tam. But he finds this, but Tam says the main difficulties are if one tentatively and approximately applies the formula he finds to the case of bound electrons, one gets a ridiculously short life value for the lifetime of an atom, and the frequency of the radiation emitted when an electron drops in a hole, he does an order of magnitude calculation and finds that you have to use the electron mass, not the proton mass, so this won't work. So Tam was probably the first one to pick up this whole, and I call it a paradigm in the Kuhnian sense. But of course there are at least 5, 6, 7, 8, 12 Kuhnian senses of paradigm, depending on which part of structure you're looking at. So when I say paradigm here, I mean it in the sense of a paradigmatic calculation, right? An example problem that someone sets out, and then someone adapts it to a new circumstance. And here, this is exactly what Tam is doing. He's using the reference as the scattering calculation from the January paper. Vladimir Fock expressed different objections, again expressing a mixture of admiration and caution. Writing on 12th February, Fock said, Dear Dr. Dirac, I thank you very much for the copy of your last paper. I read it with the greatest interest, but I cannot say that I was quite convinced by your theory. Permit me to communicate to you some doubts raised in this connection. Firstly, can the Pauli exclusion principle be applied to a continuous set of states with continuous eigenvalues? I always thought that it can only be applied to an innumerable set of states with discrete eigenvalues. For in the formulation of this principle, it seems to be necessary to numerate the states. For if the states may differ from one another by an infinitely small amount, one can never say that all the states in a region of eigenvalues, however small, are filled up. In your theory, however, you apply the exclusion principle to all states, continuous as well as discontinuous. And this is the key move for Dirac that motivates his C picture, right? Because the exclusion principle prevents all the electrons from falling into their lowest energy state, forcing some of them to pop up and behave like regular electrons. Right. And then Fock's second objection was that an infinite number of negative energy electrons per unit volume entails an infinite negative mass density all over the world. This must have astronomical consequences and may stand in conflict with the general theory of relativity. And here I think Fock is exhibiting his holism, worrying about how the different theories of physics could fit together. And roughly speaking, holism was part of the official Soviet sort of philosophy of science. And so I see a connection here between Fock's dialectical materialism and the objections that he's making to Dirac's work. Dirac replied to Fock on 21st February, but again, he didn't keep a copy, and I don't know if someone in the audience has been to the Fock archive, though I think, yeah, there we are. I don't think there's letters from this early. No. But it's possible to glean something about Dirac's reply because Dirac kept Fock's subsequent letter. Fock says, I agree that the difficulties I mentioned may be to some extent removed on the lines given in your letter. But the necessity of introducing such things as impenetrable boxes, what are they made of? The unique, really impenetrable box is a finite universe. And infinite but unobservable masses and charges seems to me a serious disadvantage of the theory. In every case, I will, quotes, wait and see. So perhaps we can see from this that Dirac, in his response to Fock, was rating that in order to have his picture, space had to be divided into these infinitesimal impenetrable boxes in order to satisfy the conditions for the Pauli principle. Fock and Tam were not the only Soviet physicists. This will be the last series of exchange I talk about. Also, Dmitry Ivanenko had a correspondence. And here's Ivanenko, Dirac, and Heisenberg later in life. Set up a correspondence during this years as well. In a letter dated 16th May 1930, Ivanenko connected Dirac's theory to a radical thought about the nature of space and time. Dirac's electron was still beset by the infinities of all relativistic quantum theories, and this is usually expressed in terms of high-frequency cutoff applied to integrals in the calculation. However, high frequency also corresponds to a short distance, and in a scattering problem, of course, short distance is the limit where the electron becomes close. Two electrons become close, two particles. And so Ivanenko writes, suppose that space is discontinuous with a certain delta x. Instead of saying that electrons cannot be closer together than the sum of their radii, we say they are sitting in these space nets, that's the words, next possible point. So not this drawing, but as if space were quantized, you see here. Ivanenko's next letter on 13th May announced his happiness about Dirac's upcoming visit to Russia that June. He says, we expect the discussion with you about the point-like space. It is unknown whether Ivanenko and Fock discussed Dirac's letter to Fock about the impenetrable boxes, but it is likely, as Ivanenko and Fock were close collaborators and explored similar questions in print. We can glean more about Dirac's thoughts along these lines from a letter from Heisenberg 3 months later on 14th July. Heisenberg says, Dear Dirac, many thanks for your few lines and the very clear poetry about, quote, quantization of space. I did not see the point in Ivanenko's paper. It seems to me that it does not contain anything more than I told in my Copenhagen lecture at, I think he says Easter here. So far, the quantization of space is no theory at all, since it leaves all questions about relativistic invariance unanswered. And so it's interesting that we had, I think it was your talk, yes, about Heisenberg's later concern with perhaps a fundamental length. So here in 1930, he's saying, so far the quantization of space is no theory at all, since it leaves all questions about relativistic invariance unanswered. I think there are two alternatives, he says. Either there is no relativistic invariance, then there might exist a shortest wavelength, and a quantization of space might be the solution. Or it is always possible to have very short waves and very high energies and relativistic invariance. In the latter case, it should be possible to construct a theory for the electron and for radiation where one puts the electromagnetic portion of the mass, the electron, to 0. But for mu equals 0, it is not possible to introduce a finite radius or anything like quantization of space. Heisenberg continued to write of their shared travels to Asia. Dirac had circumnavigated the globe, and Heisenberg was along on much of that journey. And that he was practicing the game of Go. He hoped to beat Dirac the next time they met. In a postscript, Heisenberg concluded, thinking nights and days about quantization of space. So Dirac had introduced his picture of the vacuum as an infinite density of negative energy electrons. His correspondence reveals a conversation stretching from Cambridge through Leipzig to Leningrad on possible radical consequences of Dirac's theory for the nature of space and time. Until the post-war reconfiguration of quantum electrodynamics with Schwinger, Tomonaga, and Feynman, Dirac's picture of an infinite vacuum sea would remain the physical picture. Oh, sorry, there was Fock. Here we are. Behind the modern theory here. So this is just showing a little bit of the, sorry, it's a little small, but the rhythms of the debate that I just ran through, starting from this, the summary of Dirac's work to Copenhagen, and then publications, letters, visits, Wiles papers, letters, publication, and then again, and then just over stage right, we have Anderson discovering the positron. So I'm interested in this primarily. I was interested in this for my dissertation because of the actual, the content here, the actual debate, what they were, the specific objections that these physicists were making to Dirac's theory. So I'm simply interested in that. I'm interested in how, when you read Dirac's letter, you do not get the impression that he was the, quote, strangest man, that he was unable to interact with his colleagues in a friendly manner. Perhaps in personal interactions, he had a certain style and characteristic, and that these anecdotes have become very strong and then wrapped up in semi-popular biography. But when you read the letters, you see a man who was deeply engaged with a community of physicists. He was debating with them. He was engaged in good faith. They were sharing stories. He liked to visit them in person, to go hiking, give lectures, etc. So, of course, this is one thing we all already know about correspondence, that it reveals to you a personal side of a scientist, and that is valuable for our history and our understanding of the historical actors. So that's one point I wanted to bring out from this work. But I think also there are opportunities here for some further philosophical or theoretical questions about correspondence. So we know in general that there is an interaction between the form in which knowledge is expressed and the content of that knowledge. And I'm interested to see this back and forth between an interaction between things that are expressed personally and not truly privately, because when you send a letter to Bohr, you understand that you're not just sending a letter to Bohr, but you also understand that it's not the same thing as something that will be published and sent around in preprints and mimeographs and et cetera. So it's this sort of reduced public, a public to those who have the right sort of personal access to the elites, right? And I think, I'm starting to think in this direction as something along a parallel to Polanyi's concept of tacit knowledge. Polanyi said there are certain sorts of knowledge that is really only passed around when you circulate a person, right? There's a form of knowledge that is associated with people, and so is there a form of knowledge associated with correspondence? And could this, again, be seen, because I'm interested in this sort of metaphysics, philosophy, and that interaction with published physics theory. And so is it just a coincidence that often these things are expressed in the form of letters, correspondence, or is there something else to say about that? I don't have solid conclusions, but I think the last point I want to leave you with is to say that the history of physics, the history of quantum mechanics, people in this room, we know we have great archives of correspondence, right? Correspondence letters is phenomenally important to the sorts of episodes that we in this room are concerned about. And correspondence and correspondence studies, right, is being developed, being pushed, being emphasized by other historians of science as its own sort of sub-genre, akin to visual studies, for example, of science, or akin to book history, where people are concerned about the publication of journals and circulation of texts and things like that. One very literal example of this is Janet Brown, who's the chair of my department at Harvard, is very formally trying to start something she's going to call correspondence studies. She's one of the main editors of the Darwin Correspondence Project. There's also, for example, the Tyndall Correspondence Project. We know also that for people who are interested in digital humanities, right, which, for better or worse, is rising in importance in the field, and this is also very strongly based on correspondence. So probably the most influential digital project in the history of science is Paula Finland's at Stanford, Early Modern Scientific Networks. What does this network mean? It means people who wrote letters to one another, sometimes sent a person or maybe a mathematical instrument or something. So whether or not you have sympathy to this idea that perhaps there's something like a form of knowledge associated with correspondence, I think that it is worthwhile, and I'd be very happy to hear everyone's thoughts, not just about Dirac, the debates, Heisenberg's views, or my own sort of thinking on maybe there's something sort of parallel to Polanyi, but also I see here an opportunity to make a bridge between history of quantum mechanics, history of physics, and other areas of the discipline, which I certainly feel anyway in the North American context that I mostly live in, it can be quite separate walls up at conferences and things like that between people who care about equations and people who run from equations. And so I see conclusions that we could come to from correspondence in the history of physics, history of quantum mechanics that would be relevant to other debates that are coming up in the discipline. And I wanted to just put it out there as a possibility for discussion. And that's all.
Okay, thanks a lot to Aaron. We have some 10 minutes for discussions. Ariana.
Thank you so much for this beautiful talk. I various things to say, but one point to what you were speaking about, the correspondence issue. I was wondering, for example, specifically to Dirac or this kind of writings, did you in some way try to see if there is some correlation between this correspondence and, for example, transformations in the published papers? Let's say, because to me, it's in this field, in this period, you have a transformation, the papers become more and more technical, well, maybe, and you, in earlier papers, you have more general reflections in the beginning. It depends on the author. The Dirac doesn't really, has very little of it, but throws it in some way. So my question would be, do you think it would be useful to say, try to look at the preprints? I don't know, are there preprints in this early period? I mean, how you can see the difference?
Yeah, so I think perhaps the clearest example of that would be the TAM reaction, where he sees the published paper and is part of Dirac's network, and there's a letter before the paper that is published, and then he does publish a paper, I think in the Zeitschrift für Physik, soon after, with this calculation that he first gave to Dirac. It would be interesting to see if you could distinguish between, well, is it just that there was a new idea and someone started to run with it, or whether it was really up into the correspondence. But precisely this sort of question of looking between, again, sort of what I sort of just referred to as like the rhythms between letters and correspondence. This sort of patterning, yeah, is I think a very fruitful. Yeah.
Okay, it's Michelle next.
So thank you. It was a very interesting talk. But I just wanted to address like the last point you raised, right? Because I think that's very important that we talk about this. So probably the most important thing that I've ever done and will ever do is editing Einstein's correspondence from the war years. And I have deep respect for Janet Brown. Some of my best friends are members of the Darwin industry. So I worry about like precisely this issue of communication between different parts, right? So that said, you know, like what I find off-putting is that, you know, like, so I like this, so correspondence studies, right? Now what? So this is an interesting idea. There are these rhythms, right? But what I find off-putting is that, you know, you put it like, you know, a sphere for like, what you call like, for a private sphere of like metaphysics or ontology or whatever. I mean, so there is this tendency, like in parts of the history of science community, to dress up like fairly straightforward things with a lot of historiographical flim-flam. And so I'm hoping to sort of stay away from this, right? So I think, and it seems to me that Janet Brown is somebody with 2 feet on the ground. So I think the way forward is to do like these projects, like so. Unfortunately, like in digital history of quantum, you know, like partly responsible myself, never got anywhere, but to like make these resources available and then, you know, try to find sort of the simplest language in which to express what's interesting about it, rather than sort of the most fanciful. Right?
Yeah, so I'm very conscious of the historiographic tensions, definitely, and I sort of think that because the content in history of physics and quantum is so rich, right, that I see the focus on correspondence as, regardless of whether you want to relate it to, you know, sort of the social history side or not, that because the content we have is so rich, I think if we bring it to, you know, the rest of the community, they will pay attention. So you can present the historiographical argument, right, that I think that engaging with this content and bringing it is sort of neutral on the philosophy and interpretation. There's enough there that you can bring it and say, listen, we can have these insights without this, you know, social historiography, constructionist, whatever. Like engaging with this material and I think, you know, bringing it in a non-technical way does not presuppose historiographical, you know, insight. So I hope that, yeah, we can disagree with those people, but we can have an actual disagreement over actual content that both of us are discussing, as opposed to just saying, well, those people do that and I don't like it, and them looking at physics and saying, well, I don't like that, so I don't have to go read it. Right, but so this is my position, is that there's just so much there that's relevant for history of science, period, that, you know, regardless of the slant or argument or historiography you want to bring to it, that, yeah, that it's productive, is my hope.
Okay, Shaul is next.
Not to repeat too much of Michel's. So one of my my questions here, and perhaps I also come from a little bit from the outside of the North American discourse, is that you make what you're right. There is something in the correspondence that repeats itself in different episodes in the history of different sciences. But then if we try to make my concern is that we make it too much as kind of topos of what you'll find in the correspondence. And of course the correspondence changes with time and with the topic. So I'm concerned that we can, of course, and we should discuss, make contact with other historians of science, but I think it's very important always to return and to connect that to the content of what you're doing and the specific rules of the genre, which are also changing.
Yeah, and again, I think that this is something where, as historians, we want a balance between, in some ways we see continuity, and in some ways we see specificity and individuality, but none of us want to say there is nothing in common between biology and physics, right? We study the history of science, there are commonalities, so it can only benefit us to establish what the commonalities we think are, and at the same time, of course, impose the limitations and qualifications that we believe are important. Yeah.
Two more quick questions, Alex, and then at the end. Alex is next.
So this is now a question to the content.
Mm-hmm.
So you seem to distrust the story that it was Weil's arguments that can convince Dirac, and I just wanted to, from your detailed study of the correspondence, what your feeling is as to what made Dirac abandon the whole holes are protons idea.
Right. So, so the traditional story is that Dirac had this idea. Maybe the holes are protons. He puts in print, and then in a subsequent paper, he says they can't be because they get the same mass, and he footnotes a paper by Weil. So it's not that he's not interested in Weil, but some people have put a lot of stress on Weil and mathematical rigor and the importance of mathematical rigor to Dirac, and I think that is overblown. It's just a fact that he had the letter from Heisenberg before the publications by Weil, so he knew about it. I think he cited Weil because Heisenberg didn't publish that. This was the thing you could cite, was the only thing that was in the literature, and possibly it was, a better worked out or more mathematical thing. But also in this chapter, I go into Dirac writing about approximation, the aesthetics of approximation, which he did not consider ugly. He said that all physics is like approximation. His first degree was engineering, and he continued to refer to that throughout, not just in very late life recollections, but also in the 1930s. So I think this idea of, Dirac loved mathematical beauty, but Dirac was not and did not want to be a mathematician. So that is the main corrective. The point about Heisenberg telling him before and Weil is maybe just a footnote, but for me it ties into a larger consideration of what was a mathematical physics, what was applied mathematics, what was physics, what was theoretical physics, and Dirac's self-conception.
So we're running out of time. There's one more question in the back.
It seems to me the most interesting thing of archives is working documents, drafts. For example, in the Kuhn archive, there were reviews of the Black Body book from people that weren't published. He had drafts answering for not published. So things that don't get published, Popper's disproof of quantum logic, it ended up as a half-column article in Nature. There were long articles. It seems to me it's not the correspondence, but the papers that are the important part. Do you agree?
Yeah, if they're there, great. The Dirac had a fair amount of stuff, and we take what we can, Dirac, there wasn't a lot of that sort of thing. There's some little bit. Some of it's undated, most of it sort of Cambridge era from his PhD, but not this sort of, not this era, if I recall correctly. Same with Schwinger, for example. He kept the very carefully handwritten versions that he sent to Physical Review that they returned to him, but there are no drafts. And I think there's also a self-editing of the archive, where someone has a conception of themselves as someone who presents perfectly formed arguments, and so they don't keep their drafts. But unfortunately, it's just speculation because they didn't keep them. Or the archivist, so somebody didn't keep them.
So unfortunately for space-time reasons, we have to cut off here and go over to our next speaker, which is Dennis Deeks. So thank Aaron again, and we try to set up the transparencies. I'm very glad to introduce Dennis Deeks to you, who is